In this video and the coming ones, we will present the registers and counters. We start first with the parallel load registers. Go to the details. We just would like to say that we talk first about the registers and then shift registers. After that, we start with counters, ripple counters first, and then synchronous counters, and then we consider other. Why do we talk about registers and counters? Because every computer system must necessarily include registers and counters. So you may be interested to know what is a register. The register is simply a group of flip-flops. We studied earlier that each flip-flop is capable of storing 1 bit of information. Therefore, an n-bit register can hold n bits of information and it consists of n flip-flops. A register may also contain other combination logic in addition to the flip-flops in order to determine how the information is stored into the register. On the other hand, a counter is essentially a register that goes through a predetermined sequence of states. Let us study registers and we present the simplest register, which is a 4-bit register. A 4-bit register consists of 4 flip-flops, which we call Q0, Q1, Q2, and Q3, and each one has an input, so the inputs will be named D0, D1, D2, and D3 respectively, and we call these as parallel data inputs. And then each flip-flop will have a clock input, and all the clock inputs of the 4 flip-flops will be connected to one common clock as we see in this diagram. And the common clock input triggers all flip-flops on the positive edge of each pulse. That's why in the triangle here, this says edge triggered, and it is positive edge triggered in this case. The binary data available at the inputs are transferred into the register at the rising edge of the clock like this. In addition to that, the register also has a clear input, which is asynchronous input. A clear input is connected to the R inputs of all the flip-flops, again, as we can see here, and we notice that each R has a bubble, which means it is cleared on the 0. The signal that goes to the R's is called a clear bar or a clear prime, and the bar denotes that it will clear when this signal is 0. It will clear, it means it stores zeros in the flip-flops of the register. We say that the clear is asynchronous. What does that mean? It means it is independent of the clock pulse. As soon as the clear bar is 0, the register will be cleared immediately. Let us look at a specific example where the clear signal is 0, as we see here. This we call timing diagram. And when clear is 0, the outputs of the flip-flops will immediately become all zeros. So Q0 is 0, Q1 is 0, Q2 is 0, and Q3 is 0. And we say that flip-flops or the register is cleared. They will remain 0 until the following happens. First, a clear bar must go back to 1. So from 0, we put it at 1. Second, the clock must go from 0 to 1. And at the edge of the clock here exactly, the inputs of the flip-flops will be transferred to the outputs. So we see here that D0 is 0 and D3 is 0. Therefore, at this point in time exactly, Q0 will continue to be 0 and Q3 will continue to be 0. On the other hand, D1 is 1 and D2 is 1. Therefore, Q1 will take the value 1 here, and Q2 will take the value 1 also here, exactly at the rising edge of the clock, and the values of the outputs will be 0, 1, 1, 0, similar to the inputs of the flip-flop. And we said that the data is stored in the... Now we look at another register which has additional input. It is a specific control signal that we can use to load or not load the register. We call it register with parallel load. Let us see how does it function. Same thing, the diagram has 4 flip-flops, A0, A1, A2, and A3, and we have combinational circuits at the inputs of the flip-flops as we see here on the left-hand side. Let us assume the load is 0. So if this is 0, this will be 1, and this is 0. So this is 1, 1, 1. This will be 1, and 1, 1 here, 1 here. And the 0 will be inputs, these inputs to the AND gates. Therefore, these outputs will be 0 here, and 0 here, and 0, and 0. And the other AND gates will produce A0 here, and A1 here, and A2 here, and A3 here. And therefore, the Ds of the flip-flops will be as follows. This will be A0, and this will be A1, and this is A2, and this is A3. Now, what will happen when the clock pulse goes from 0 to 1, which is the rising edge of the clock? All flip-flop inputs will be loaded in the flip-flops. Therefore, A0, A1, A2, A3 will be maintained. We say for this case, when load equals 0, the register retains the data. So that's now we understand. On the other hand, when load is equal to 1, the register will accept the new data. That's why load is true, so it loads the input data. Let us make load equal to 1, so we'll change the signal. This will be 1, and this will be 0, and this will be 1 here, and this will be 0, this will be 0, this will be 0. Again, please follow me with the inputs of the AND gates. We have changed them. And the other AND gate, this will be 1 here, 1, 1, and 1. Therefore, this will be 1, and this will be 1, and this is 1, and this is 1. The result, the AND gates, this will be 0, and this will be I0 here, because 1 and I0 is I0. This will be 0, and this will be I1, and this will be 0, and this will be I2, and this is 0, and this is I3. Now the outputs of the OR gates, this will be I0, and this will be I1, and this will be I2, this will be I3. Again, what will happen when the clock pulse goes from 0 to 1 at the rising edge of the clock? The inputs of the flip-flops will be stored in the flip-flops. Therefore, I0 will be here, and I1 will appear here, I2 will appear here, and I3 will appear here. Therefore, to summarize, when the load is 1, the inputs I0, I1, I2, I3, which we call them parallel inputs, will be stored and appear at the outputs of the flip-flops. They will appear exactly at the rising edge of the clock. And when load is equal to 0, no change in the register will take place, which means the register will keep the same data it has before.